After more than 2 years of development, capped off by 7 months of silence from the launch pad, SpaceX is finally ready to launch its massively upgraded version 3 Starship. 2 vehicles featuring so many changes, they might as well change the name altogether. And while that is exciting, depending on when you watch this, Booster 19 and Ship 39 may already be a distant memory. Thousands of them, in fact, scattered across the ocean floor. The launch pad, however, well, after all the steam settles, it'll still be here. Which means, unlike the other 2 characters in the story, Stage 0 2.0 has an extremely important job to do: survive. Because, with minimal refurbishment, it's gonna have to turn around and do this again, and again, and again, hundreds, if not thousands of times throughout its operational lifespan. After 5 years of R&D, SpaceX built their new pad around a proper flame trench, with a beautifully built deflector system, a water-cooled launch deck, and heavily reinforced external shielding covering not just some, but all of the critical GSE components. But there was still one major problem that SpaceX needed to solve before this launch pad could become rapidly reusable. They needed water. Lots and lots of water. More water delivered at a higher flow rate and pressure than any other launch pad on the planet. But instead of simply expanding on the systems they had developed for the R&D launch mount or the static fire test stand at Massey's, they decided to take a radically different approach. One that replaces giant banks of pre-charged nitrogen cylinders or nearly 500,000 pounds of heat exchangers with something far more compact, far more violent, and far less forgiving. Buried inside of this system are 9 Methalox-powered flamethrowers, whose entire job is to create an absurd amount of pressure almost instantly. If it works, this could be remembered as one of the greatest innovations in Launch Pad GSE design. And if it doesn't, it could become one of the most complicated liabilities ever bolted to a water tank. By now, there's a good chance you may have heard about these mysterious new gas generators that SpaceX is using to power their water deluge system. But considering they have yet to publicly acknowledge their existence, there's virtually zero information about them. Luckily, we're going to fix that problem today. So if you've been curious how this insane new system actually works, and how a handful of shop vacuum-sized devices are being used to move nearly 1 million gallons of water in less than 60 seconds, then trust me, you've come to the right place. But for now, I think it's best that you forget what you've seen here, and discover the system the same way that we did. One clue at a time. Hey, by the way, don't forget to hit the ignition on that subscribe button below. My name is Zach Golden, and this is another CSI Starbase Deep Dive Investigation. Hey everyone, welcome and thanks for joining us for part 3 of the Stage 0 2.0 Ultra Deep Dive series. In the first 2 episodes, we covered the design and construction of the subsurface flame trench, along with the components that make up the flame deflector system that should allow Starship to launch repeatedly without major pad refurbishments. And honestly, if we would have gone into any more detail than we did, SpaceX probably would have ended up with a flood of applications from people who suddenly think they're qualified to be Stage 0 project managers. And who knows? I'm sure some of you probably are. My goal with this episode was to make it easy to follow even if you haven't seen the first 2 parts, but I do highly recommend watching them afterward, because as far as I know, this is the most detailed series ever made about the design and construction of any launch pad on the planet, whether it's past, present, and probably the future too. Unless SpaceX decides to release their own 5-hour documentary. Today, with the help from Knaggs, who modeled the entire launch pad and water deluge farm over the past year, and Ryan Hansen Space, who created the most detailed renders and animations of this new gas generation system that you will ever see, we're going to take a deep dive into the incredible water delivery system that SpaceX developed for its brand new launch pad. Originally, this was supposed to include both the design and operational sequence of the system. But once the episode started pushing 3 hours, I realized that it needed to be split in half. So in part 3, we're focusing on the design and construction of the water delivery system. In part 4, we will go even deeper into how all of this actually works during the testing and launch operations. As much as I hate breaking up the complete uninterrupted storyline, it was important for me to get this part out before Flight 12. And on that note, before we get started, I want to sincerely thank everyone who donated through PayPal after the last episode. Without that support, I probably wouldn't have been able to release 2 episodes in a row without a sponsor. As much as we do rely on those sponsor ads, getting this out before Flight 12 was the higher priority. So I really do appreciate everyone's generosity, especially with everything going on economically right now. It really means a lot to us. So I guess we can say this episode is brought to you by our incredible audience. Alright, with that said, let's jump right back into the investigation and pick up exactly where we left off. The amount of engineering and design work that went into the flame trench, deflector system, and launch mount is incredibly impressive. Without a doubt, I'd say that Stage 0 2.0 looks like it was successfully designed to be as close to indestructible as a launch pad can realistically get. But that only remains true if the system we're about to cover today actually does its job. Because all of that protection depends on SpaceX being able to deliver hundreds of thousands of gallons of water to the right places at the right time at an absolutely ridiculous pressure and flow rate. And as we're about to see, the method they chose to do that is not exactly the conservative option. It is compact, aggressive, and extremely clever, but it also comes with a lot of risk. So before we get into the incredibly unique gas generation system, there are a few things we need to cover first. Starting with the storage tanks and the distribution system that actually delivers all of that water to where it needs to go. When we look back at the static fire test stand, there is one water tank connected to a 30-inch pipe that supplies the middle section of the flame deflector. There are two additional tanks supplying water through a 48-inch pipe that gets split between the two outer sections. As I mentioned before, the dual flame deflectors for the launch complex are roughly the same size, both consisting of 66 pipes. Instead of being broken into multiple manifold sections with two separate supplies, both of the deflector ramps are treated as one component and have a single shared water source. In March of 2025, while the massive concrete work for the floor of the trench was ongoing, workers began excavating a 30-foot deep trench for the main water supply. At the floor of the trench is a thin concrete slab which acts as a small water barrier, but mostly just gave them a flat surface for the pipe run. After laying a path of steel beams for them to rest on, the massive 4 and 5-foot diameter pipes were installed between the trench and the water farm, and then fully encased in concrete before backfilling the trench. Before reaching the trench wall, the larger 60-inch pipe splits into two smaller 48-inch pipes to supply both sides of the flame deflector. By this point, the flame deflector and apex manifold had been installed, and short pipe sections were inserted through the sleeves in the speed core walls to extend the manifold inlets out past the trench wall. These transition sections reduced the incoming 48-inch supply down to 42 inches for the deflectors, while the apex manifold sees an even more aggressive reduction from 48 inches down to 24. Reducing the supply to match the diameter of the respective water manifolds inherently limits the flow of water into those manifolds in the process. Some of you may be wondering, why not just run the smaller diameter pipes for the entire length? Well, to explain this, let's assume you're supplying water at 200,000 gallons per minute. In a straight 48-inch pipe, the water would be traveling at roughly 35 feet per second, or about 25 miles per hour. With the same volumetric flow rate in a smaller 36-inch pipe, it jumps up to 63 feet per second, which is over 43 miles per hour. That higher flow rate results in more turbulence and wear on the pipes, and the pressure drop across the length of the pipe run will be about 4 times greater due to increased friction. Using an oversized pipe greatly reduces the overall pressure losses in the supply line, which means you need less head pressure in the water tanks to achieve the same desired pressure at the inlet of the manifold. Anyway, back at the water farm, in order to enable each component of the Deluge system to operate independently of each other, the bulk storage tanks are arranged in 3 separate groups. The first group of extra-large water tanks is used to supply the dual flame deflectors. These appear to be identical to the Deluge tanks at Massey's, which would give them a capacity of 89,400 gallons. After adding a 5th tank to this group, the total water available for the flame deflectors is just under 450,000 gallons. To put that into perspective, that's roughly equivalent to the capacity of the water tower at Launch Complex 39B. In other words, the flame deflector system on its own carries as much water as the entire Deluge system supporting SLS. Next, there are a group of 3 smaller tanks that feed the apex manifold, and a final group of 3 for the water-cooled launch deck. Each of these tanks hold an estimated 59,000 gallons, which means both systems have a capacity of roughly 177,000 gallons. When you add all of this together, the total capacity of the combined system is just over 800,000 gallons, easily making this the largest water Deluge system ever built, exceeding its closest competitor by 50,000 gallons. And before anybody says anything, the system at Stennis doesn't count because the reservoir feeds more than one test stand. Unlike the Deluge system for the static fire test stand, but similar to the one for Pad A, there are no control valves on any of the discharge manifolds. Instead, there is a 60 and a 48-inch weir pipe installed immediately downstream of the combined discharge manifolds for the flame deflector and apex system storage tanks. These weir pipes eliminate the need for large control valves by raising the flow path above the maximum height of the water in the tanks. Under normal conditions, the water will never reach above this height in the weir unless it's forced out under pressure. When the system is activated and water begins flowing over the top of the weir, there will initially be a large pocket of air trapped inside of the pipe. At the top of each weir is a vent that allows the air to escape as the pipe rapidly fills with water and also acts as an anti-siphoning vent or a siphon breaker. This is an important feature because the flame deflector and apex manifold both sit lower than the outlet of the water tanks. If left unmitigated, that elevation difference would allow water to continue siphoning from the tanks even after the system is shut down, which would eventually drain them completely. To prevent this, the relief valves are opened immediately after shutdown, allowing air to flow back into the pipes and quickly break the siphon. After connecting the far side of the weirs to the underground pipe run and backfilling the trench for the primary supply pipes, crews began laying a group of pipes for the secondary and auxiliary water systems. This includes a large 48-inch pipe with a rack mounted on top for carrying 6 smaller 10-inch pipes. Just like the supply for the other 3 manifolds, after reaching the trench wall, the larger 48-inch pipe reduces down to 36 inches before entering the square manifold for the water-cooled launch deck. The collection of 10-inch pipes attached to the supply for the launch deck are for things that I would consider to be auxiliary systems, so we will discuss those more later. Running parallel to this bundled group is a mid-sized 36-inch line that reduces to 24 inches as it turns upwards towards the surface. As of the time of this episode, it's still not connected to anything. Rather than speculate on its exact purpose, the important detail is where it's supplied from. When we trace it back to the source, it's obvious that it will eventually tie into a T at the base of the larger 60-inch weir pipe. Because the primary flame deflector supply does not have an isolation valve, there's no way to divert flow exclusively to this branch. That means whatever system this line will eventually feed into will activate at the same time as the flame deflector prior to ignition. In other words, any future system connected here would draw from the same water source and reduce the available capacity of the primary Deluge system. Of course, additional tank capacity could always be added if necessary. Anyway, as I mentioned before, the 48-inch pipe for the water-cooled deck is supplied by the third group of water tanks. The discharge manifold for these tanks runs beneath the second group. As you may have noticed, it does not use a weir pipe, and instead, the discharge manifold runs flat across the ground before dipping below grade after passing through this missing pipe section. Unlike the situation with the flame deflector and the apex manifold, the perforated surface for the water-cooled launch deck is several feet above the water storage tanks. Because there are no valves, the height of the water in this riser will always be equal to the height of the water in the tanks unless it's forced out under pressure. And as soon as the system is depressurized, the water will stop flowing without the need to break a siphon. Before we move on, I know some of you are wondering how all of this water is being supplied. Because as I mentioned in part 1, utilities have always been one of the biggest operational bottlenecks at Starbase. So let's quickly take a look at that. Over the past 3 or 4 years, SpaceX has made major investments to systematically eliminate constraints in the supply chain of consumable commodities at Starbase. Dedicated 3-phase power lines, backed by an ever-growing fleet of Tesla Megapacks, have replaced the original off-grid setup. And for cryogenic commodities, an on-site air separation unit is currently under construction and will eventually supply nitrogen and oxygen directly. But that ASU will require a massive continuous power draw, likely exceeding the baseline capacity of the 2024 power upgrades. So even though construction is underway, I have a feeling it may be more than a year before we see it fully activated, as an additional transmission line from Brownsville could be required. But if they really want to shorten that timeline, they could potentially tap into the existing power supply for Pad A, which will not be needed again until sometime next year. While that is less than ideal, a new Lind ASU has recently come online in Brownsville and can supply nitrogen and oxygen in the meantime. This alone should eliminate at least 500 12-hour round trips to Houston for each launch cycle, which is a major logistical win. As far as we know, there are also long-term plans for a methane pipeline connecting Starbase to the new LNG facility at the Port of Brownsville. But between permitting and construction, that could take years before it's completed. The most immediate and impactful upgrade, however, is water. Unlike the launch sites at Cape Canaveral, which have access to a robust municipal and industrial water distribution network capable of supplying large volumes of water on demand, Starbase has historically operated as a largely off-the-grid facility when it comes to potable water. For Pad A, Deluge water was trucked in from Brownsville. Even with the ability to offload 4 tankers at a time, a last-second scrub after Deluge activation meant a 24-hour turnaround time just to refill the tanks. That model simply doesn't scale with the flight cadence they're targeting. In March of 2025, contractors began installing a permanent underground water line between Brownsville and the launch complex. This long-overdue utilities project uses trench-laid blue PVC pipe where excavation is practical, and long, heat-fused HDPE tubing installed via directional drilling along Highway 4 in areas where adjacent waterways make open trenching impractical. That line doesn't just serve the launch site, it also feeds the ASU, which will require a continuous supply of up to 650 gallons a minute for cooling purposes. And if you trace it back to Brownsville, it has branches feeding the Starbase village, the main water storage for the production facility, and all of their other facilities and housing developments along Highway 4, including the water tanks for the static fire test stand at Massey's. This massive infrastructure project has been underway for well over a year, and based on aerial imagery, it appears to be in its final stages, and it may potentially be completed within the next 6 months. Once fully operational, it will allow the launch complex to replenish water in hours instead of days, which will dramatically reduce the turnaround time and further reduce the number of heavy transport vehicles on the highway. And as launch cadence climbs beyond the 25 flight per year limit, that shift from trucked-in water supply to continuous utility infrastructure won't just be convenient, it will be essential. But while waiting for the municipal water line to come online, SpaceX needed a temporary fill station so they could begin testing the Deluge system immediately. Instead of creating a simple stopgap solution, from the start, it was designed to tie directly into the permanent infrastructure once the new supply became available. Next to the main group of water tanks, a 13-port fill station was installed, which appeared to give them more than 3 times the offloading capacity of Pad 1. But we will come back to that shortly. Because tanker trucks don't typically rely on their own pumps, this manifold feeds into a group of 3 pumps beneath the first water tank. From there, water is routed through a 4-way valve manifold that distributes the flow to each of the independent storage systems. The first valve fills the vertical Firex tanks from the bottom through the shared discharge manifold instead of having a dedicated inlet for each tank. The second valve on the selection manifold has a line running into the side of the larger 60-inch weir for the flame bucket distribution system. Because these tanks share a valveless discharge manifold, water first fills the manifold to the base of the weir and then begins filling all 5 tanks simultaneously. Forming a bridge between the 2 sides of the weir is a small prime-up line running across the ground. Once the level of water in the tanks is above this point, a valve will open up to allow water to begin siphoning over to the other side of the weir to flood the underground pipes. This avoids the need to waste stored water just to prime up the system. Ideally, this pre-fill should stop before the water reaches the trench wall penetration, or else water will begin flowing out of the flame deflector. This system is essentially duplicated for the Apex manifold distribution system. The third valve in line sends water to the tank side of the weir, filling the middle group of tanks from the bottom. And just like the first system, you can see the prime-up line bridging the 2 sides of the weir running along the ground. Finally, the fourth valve sends water into the discharge manifold for the water-cooled deck system. In this case, because of the lack of a siphon-breaking weir, the water first fills the 48-inch supply line up to the riser on the side of the trench wall before it begins filling the 3 conjoined tanks. But because the launch deck sits higher than the top of the water tanks, the water will not rise high enough to fully flood the pancake structure without some additional help. And that's important because just like the equivalent water-cooled plate for Pad 1, they will want to fill the entire pancake structure until the water is coming out of the holes in the surface. That way, when the system is activated, it begins ejecting water immediately and avoids the internal shock loads as the water violently enters the plate. To reach that height, the underground supply line is isolated from the storage tanks using what appears to be a custom-made double-flanged dual-plate check valve. As the name implies, this valve is designed to be mounted in line between 2 flanges, which gives it a short cylindrical appearance that makes it look more like some kind of expansion joint. Inside the housing are 2 spring-loaded semicircular plates that swing open once the flow is moving in the forward direction. As soon as the flow attempts to reverse, those plates snap shut and prevent the water from flowing backwards through the system almost immediately. Adjacent to that valve is a pair of pumps that transfer water across the check valve, allowing the automated system to slowly fill the riser and launch deck without activating the gas generator system. Before we move on, there's one strange detail about the fill station that's worth mentioning, mainly in the hopes that someone in the comments might have an explanation. When it came time to begin filling the tanks with water, the 13-port manifold wasn't used at all, which I guess isn't entirely surprising given that it's installed in a location where there's barely enough room for a single truck, let alone 13 to maneuver safely. Instead of relocating it to a more logical position on the opposite side of the blast wall, they simply ran a long hose to that area where an adapter allows 3 trucks to offload simultaneously. This is extremely confusing and has been bothering me for months. At this point, I'm willing to send the first person in the comments to come up with a legit explanation a free Stage 0 2.0 t-shirt. To everyone else, in the spirit of the upcoming Flight 12, which may have already happened by the time you watch this, we will add these to the existing 15% discount in the CSI Starbase merch store. So if you want to pick up one for yourself, just type in the code GRACKLEFTW during checkout. That might not make sense now, but it will shortly. Anyway, in mid-January, as it was in the early stages of recording this, SpaceX began installing the remaining distribution plumbing for the future municipal water supply. I swear, this happens every single episode. I rarely regret how long these videos take to release, because if I had published this 8 months ago as I originally planned, a huge piece of the puzzle would have been missing. Emerging from the ground near the massive H-shaped GSE pipe rack, we can now see the new municipal supply line routed across the rack before heading back underground. After reappearing behind the Firex storage tanks, it runs across the blast wall and then turns to run alongside the 60-inch water manifold. From there, it tees off in 2 directions. One branch connects directly to the far side of the 4-way valve manifold, meaning that manifold now has the temporary tanker supply on one side and the permanent municipal supply on the other. That means as soon as the municipal supply comes online, that transition will be seamless. And the only way we will even know it happened is when we all of a sudden realize that it's been weeks since the last time we saw a water truck. The second branch runs across to a pump skid beneath the smaller group of water tanks. Notably, these are much larger than any of the other pumps within the water farm. From there, it enters an underground concrete embedded line that runs past the flame trench and over to the far side of the retention pond. At the deep end of the pond, there is currently a U-shaped bridge connection tying the end of this water line into the existing drain valve. That strongly suggests that this may be the location where the entire 15-mile municipal line from Brownsville will be flushed once it goes active. For a potable water source, that would make a lot of sense. On that note, the activation of this system may actually be more obvious than I previously suggested. Initially, we thought this might be preparation for a future pump system to recover runoff water from the pond. But if that were the case, the pipe would likely be green rather than blue, since blue is typically reserved for potable water supply. Beyond that, the pumps are located in the exact opposite location of where they should be if their intended purpose was to drain the swamp. So this appears to be groundwork for future expansion, which has been strategically routed so that it can serve as the discharge point for the municipal line during commissioning. Looking at the future site plans, we can see 2 different water storage areas that don't exist yet. Well, technically there's 3 if you include Water Storage 2 at the D1 entrance. Within the expansion zone, there's Water Storage 1, which is likely associated with the LNG liquefaction facility. And of course, there's also Deflector Farm 1 for the original pad upgrade. And somehow I'm only just now realizing that this is the first official documentation referring to them as Pad 1 and Pad 2 instead of A and B. Well, I said I wouldn't change my own naming scheme until it happened, and here we are. Anyway, unless we see another parallel underground line appear next to this one, it doesn't look like SpaceX plans to actively recover water from the retention pond. With that said, since there is a drain at the deep end of the pond, it is possible that we could see a future filtration system added, allowing some level of water reuse down the road. On that note, this is probably as good a time as any to look back on our list from Part 1 and discuss another pain point from the original launch pad design: the retention pond. When we look at the early site plans from 2020, we can see that it showed an extremely large retention pond, one that appeared to be capable of capturing and storing far more water than the eventual Deluge system would end up discharging. Its scale also suggests that it was intended to manage general pad runoff during heavy rain events as well. But as you know, those early plans relied on access to the expanded property boundaries, which simply wasn't available until February of this year. So what ultimately got built behind the integration tower was far more modest. While it was theoretically large enough to hold most of the 370,000 gallons stored in the Deluge tanks, only about 1/6 of the water discharged by the booster bidet system was actually directed towards the pond. The rest was blasted 50 to 100 meters into the surrounding wetlands or thrown back onto the pad itself. Even if the pad had been perfectly graded to funnel runoff water towards the pond, the maximum recoverable volume would have likely been somewhere between 20 and 40%. And based on what we observed after tests, even that may have been generous. In practice, the pond functioned more as stormwater management than a true deluge recovery system. And because it also collected pad runoff, oils, particulates, concrete dust, and combustion byproducts, the water would have been classified more like industrial process water than a reusable supply. That likely explains why no recirculation system was ever installed to pump it back into the storage tanks. Instead, it was removed by vacuum trucks and hauled off-site. This meant that if the Deluge system was activated during a last-second abort, crews weren't just resetting valves, they were effectively starting from scratch. Now, considering the near-flawless execution of the terminal countdown on all 11 flight tests, this never became a true operational problem. But it was mentioned in nearly every broadcast as something to keep in mind. One major benefit of developing a subsurface flame trench is that it effectively becomes a massive retention basin for the water discharged by the flame deflector and the apex manifold. As we saw during testing, while some water escapes beyond the property boundary, the vast majority remains inside of the enormous concrete bathtub. And this is where the sump system comes into play. Those of you who watched the Starship Flame Trench episode will remember the sump pump and speculative filtration system housed inside of a box in the corner next to the step. A similar system was built into the flame trench for Stage 0 2.0, except this time, the sump is integrated directly into the floor. You may have noticed that I intentionally skipped this topic in parts 1 and 2. I thought it made a bit more sense to wait until now, since it will become more relevant. As the embed plates for the trench walls and flame bucket supports were being laid out, 4 cylindrical sump pits were inserted down into the rebar cage. You can see that each pair consists of a large sump pump paired with another that is about half the size. Thanks to some well-placed images, I was able to find a spec sheet for the primary pumps, which lists their capacity at 1,700 gallons per minute. I wasn't able to identify the smaller pumps, but I'm assuming they're about 1/3 to half the capacity of the larger ones. The smaller pumps sit within the 8-inch deep basin at the floor of the trench, while the primary pump housings are mounted flush with the finished floor slab. The water discharged by the secondary pump tees into the primary output, and all 4 systems combine before exiting through the trench wall. From there, the return line runs alongside the Firex supply lines back to the water farm. Based on the routing, we can now confirm that this return line feeds back into one of the large tanks in the flame deflector storage group. The water equalizes across the 5 interconnected tanks through the valveless discharge manifold, which means you only need to fill this one tank. With the combined output from all 4 pumps, the system should be able to empty 450,000 gallons out of the trench in roughly 90 minutes. This means in a last-second abort scenario, where the system would shut down quickly after activation, the turnaround time could realistically drop to less than 20 minutes. This recovery capability also opens up interesting possibilities post-launch. Because the Deluge system continues running for 15 to 20 seconds after liftoff, there could easily be 50 to 100,000 gallons remaining in the trench. In the roughly 7 minutes it takes for the booster to return, the sump could recover somewhere on the order of 30 to 40,000 gallons. When you combine that with the continuous municipal water supply, there should be a significant increase in the amount of water available for the secondary activation. The only caveat is that during final approach, the flame bucket is unlikely to be the active system. Instead, that responsibility would fall to the water-cooled launch deck. So for a full mid-flight replenishment to be useful, there would need to be a transfer path between the deflector storage tanks and the water-cooled deck tanks. At the moment, there's no clear evidence of cross-feed capability between the 3 tank groups, although there are a few pumps in the Deluge farm whose function remains unclear. But I'm fairly confident they have nothing to do with that. Regardless, the combination of trench recovery and municipal refill dramatically reduces turnaround time and allows the system to discharge more aggressively during liftoff, without the previous constraint of reserving water for a potential second activation. Alright, now returning to where we left off with the massively upgraded water distribution system, the most difficult component of this entire system to reverse engineer is not only the most important, but in my opinion is perhaps the most interesting as well. In fact, for some of you, this may have been the entire reason you were waiting for the series in the first place. Hopefully that group is small, because I doubt many of them would have made it this far. But if you're still here, I hope you've discovered a few things that you didn't even realize you were interested in along the way. Now that we've covered the water supply, the bulk storage, and distribution systems, the real question we need to answer is, how do you move all of that water from point A to point B in less than 60 seconds? As I mentioned in the Starship Flame Trench episode, by the time Stage 0 2.0 was being designed, SpaceX was already several years deep into a rarely discussed internal R&D effort focused entirely on solving a problem that was arguably completely self-imposed. All right, look, everybody already knows where I stand on this situation. We're trying to get to Mars, okay? And we're not going to do that by following in the footsteps of anybody else out there. All right? So I say that. Let's focus on getting Falcon 9 reliable for now, but eventually, we're gonna need to innovate water. For more than 60 years, most of the spaceflight industry has relied on massive diesel-powered industrial water pumps or towering gravity-fed water reservoirs to generate the head pressure required for their sound suppression systems. Clearly despising the industry standard, SpaceX has pioneered the use of innovative high-pressure gas-driven systems. Since the early days of Falcon 9, they've continued to iterate that concept in search of a more compact and responsive way to generate high-pressure gas on demand. When you consider all three components of the Pad 2 Deluge system operating simultaneously, the combined flow rate likely approaches 800,000 gallons per minute. And just to be clear, that's a slightly conservative estimate. If SpaceX were to come out and tell us that the maximum flow rate is actually closer to 1.6 million gallons per minute, I would not be surprised. In comparison, before it was deleted, the Pad 1 deflector farm had a storage capacity of 370,000 gallons. Using 110 high-pressure nitrogen gas cylinders, they were able to displace about 450,000 gallons per minute. That's roughly equivalent to what we would expect from just the two flame deflectors, or about half the total system demand of Pad 2. Simply duplicating the Pad 1 gas system for Pad 2 would require roughly twice as many pre-charged cylinders, if not more. It would likely resemble the system at SLC-40, which, relative to Falcon 9's requirements, appears dramatically oversized. Honestly, this looks a lot more like what I would expect to see on a launch pad designed for Falcon 27. While the increased footprint of the system could become a minor issue, I think the real limitation isn't space, but thermodynamics. When you rapidly compress a gas inside of a fixed volume cylinder, the temperature rises sharply. This effect is known as adiabatic heating. The faster the compression, the greater the temperature increases. You've likely experienced the inverse of this if you've ever rapidly discharged a can of compressed air. The container becomes extremely cold. That is adiabatic cooling, which is the same physics just in the opposite direction. So in order to prevent thermal stress and allow the heat to dissipate through the cylinder walls, the recharge process must be slow and carefully managed. And that inherently limits how quickly the system can recycle between activations. This is a concept that we will more than likely revisit when we discuss the V3 booster and ship. Given the continued evolution we've observed since that system was installed, I think it's safe to assume that the engineering team strongly disliked the system from the very beginning on a personal level. But leading up to and following Flight 1, their goal was to get the booster bidet system operational as quickly as possible, so it was probably a matter of convenience to reuse as much as the original Starship Deluge system from LC-39A as they could. By the time construction began on the Starship flame trench, they were able to implement a new approach that effectively rendered the original high-pressure storage model obsolete. Instead of relying on large banks of pre-charged gas cylinders that take hours, if not days to refill, the upgraded system for the Massey's test stand was able to generate high-pressure gas in real time. By diverting a portion of the water supply and using it to vaporize liquid nitrogen inside of 3 recirculating cryogenic heat exchangers, the system can actively generate enough gas to sustain a continuous flow rate of roughly 200,000 gallons of water per minute. While less powerful than the system for Pad 1, it could easily be scaled up if needed. And here's something I didn't mention in the Starship Flame Trench episode. This system is actually a scaled-up version of something they were already running for years at the orbital tank farm. I think after all this time, this is still a relatively unknown fact, and I've been waiting a very long time to talk about it. Inside the original fluids bunker were 6 relatively small water recirculating cryogenic vaporizers, installed during the earliest phases of tank farm construction. These were arguably among the most important components of the entire system, because they managed the ullage pressure inside of the storage tanks while propellant was rapidly transferred into the vehicles. Think of it like an autogenous pressurization system for the GSE tanks. What's especially interesting is that this setup supported all of the vertical LOX and liquid nitrogen tanks, as well as the horizontal methane tanks. Have you ever wondered why they had such a massive water tank long before a deluge system even existed? Or why the unused methane tanks were immediately converted into water storage after the original water tank was compromised? Well, that water wasn't just sitting there waiting for a fraction of its capacity to be used for fire suppression. Nah. It was functioning as a massive thermal energy reservoir for the water recirculating vaporizers. Using multiple large water pumps, which are just barely visible here, water was pumped through the heat exchangers and back up into the top of the water tanks. In the early days, the propellant loading process took roughly 90 minutes to complete. That likely meant recycling a substantial portion, if not the entire volume of that water tank, through the heat exchangers during a single load cycle. And the further they would progress into that propellant loading cycle, the colder that water would become. This was something that had to be carefully managed because as the temperature of the water decreases, it degrades the heat transfer performance inside of the vaporizers. To counter this, SpaceX installed a natural gas-fired heater system that diverted part of the circulating water through a heater before returning it to the tank. Rather than injecting small amounts of water mid-load, it's likely that they began preheating the entire water mass hours or even possibly days before testing. I wouldn't be surprised if it ran continuously in the early phases of the program. That entire system was eventually replaced with several large banks of forced draft ambient air vaporizers sometime during the 4th or 5th major tank farm overhaul. Honestly, I've kind of lost track at this point. I'm not sure if you're able to truly appreciate this from pictures alone, but these vaporizers are absolutely massive. So it's no wonder they originally tried to go with an approach that would reduce the overall footprint of the tank farm. To put this into perspective, 6 of these small water recirculating heat exchangers can basically fit inside of the footprint of 2 ambient air vaporizers. The new tank farm uses 18 of these vaporizers for the pressure building system. But when you consider the fact that they've essentially doubled the pump capacity here, as a rough estimate, let's just say that you need 9 of these vaporizers to accomplish the same task. In my opinion, it seems obvious that this system clearly paved the way for what we now see at Massey's, just scaled and optimized for a different mission profile. There are 2 key differences here. First, the Massey's system must generate significantly more gas in a much shorter window of time. That's why it uses 3 or 4 much larger heat exchangers, likely 10 to 15 times larger than the original bunker units. Second, it only operates for about a minute at a time and doesn't recirculate chilled water back into storage. Because of that, it doesn't require the continuous recirculating heater system. In some ways, it's actually simpler, just built around much larger components. Now, implementing the same type of active gas generation system at Pad 2 would require roughly 5 times the number of high-capacity vaporizers to meet the demand. And because these systems are independent of each other, each group of tanks would require its own heat exchanger loop, with those 15 vaporizers proportionally divided between the 3 groups. For the most part, there's no reason a system like this shouldn't work, and the footprint wouldn't be excessively large either. But as the water deluge farm began to take shape, it quickly became obvious that SpaceX had pivoted to a new method of supplying high-pressure gas to the water tanks once again. Before we jump into reverse engineering this new gas generation system, there's something important we need to address. Because the hardware that started appearing in early 2025 didn't just signal a new design, it signaled a shift in who was building it. And that major shift tells us a lot about where SpaceX is as an organization. In January of 2025, as the flame trench excavation was underway, crews began installing the first components of what was clearly a new gas generation system. This included vertical cryogenic storage tanks, banks of high-pressure gas cylinders, and a narrow trench routing towards them, which would later prove to be a critical clue in understanding how this system actually works. 2 months later, after the first water tanks were being set in place, a second, smaller pair of vertical tanks arrived, along with another bank of high-pressure gas cylinders. At first glance, this looked like the early stages of a scaled-up version of the water recirculating vaporizer system developed by the team at SpaceX's McGregor facility. But that was until the prefabricated pipe racks began arriving. And that's when we realized that the distinct fingerprints found all over the system did not belong to McGregor. The entire build philosophy, fabrication approach, and level of modular prefabrication pointed somewhere else entirely. For those who were paying attention, it was clear that a different team had taken the lead on this system, and that transition marks an important phase in SpaceX's evolution. So before we continue, it's worth introducing the group now playing a major role in shaping the next generation of launch pad development. Outside of Starbase, the McGregor, Texas facility is one of the most observed SpaceX sites, which means over the years, we've been able to closely track their activities thanks to periodic flyovers by NSF. With that said, historically, the team at McGregor has specialized in propulsion testing and the development of ground support systems. They also manufacture all engine-related hardware, which pretty much includes everything other than the engines themselves, along with vehicle integration and transportation systems. In addition, they also appear to be primarily responsible for designing and fabricating test stand infrastructure. When it comes to test stand infrastructure, these are typically one-off structures designed to accomplish a very specific task and are often reconfigured for another purpose once that task is complete. During the experimental phase of Starship development, which we're still kind of in but slowly working out of, including Launch Pad GSE development in their list of responsibilities made perfect sense. But as the program has matured, SpaceX has entered a distinctly different phase, one heavily focused on rapid reusability while simultaneously expanding their existing launch infrastructure from a single operational Starship pad to 5. So with 5 launch pads currently in various stages of completion, and more almost guaranteed to be announced in the coming years, SpaceX needed a team specifically dedicated to producing modular, repeatable, and scalable GSE systems. And to streamline this immense expansion effort, those systems need to be built more like standardized products on an assembly line, not one-off custom structures, and with as much off-site prefabrication as possible. Thankfully for us, the results of that shift played out in a location where we could actually witness it. Because good lord, the execution of that strategy was absolutely incredible and was on full display during the most recent phase of the orbital tank farm expansion. Compared to phase 1 back in 2021, it looked less like a custom fabrication project and more like assembling a colossal Starship-branded IKEA set. Valve skids and pump assemblies began arriving on site with control panels and plumbing already installed, dramatically reducing the amount of work required in the field. As these prefabricated components continued to show up, I couldn't help but wonder where they were coming from. So in March of 2025, I reached out to Greg Scott and asked him to do a flyover of a SpaceX facility that we hadn't checked on in years. Longtime followers of the program might remember the original Starship development site on Sidco Road in Cocoa, Florida. Long assumed to be mostly inactive, what we found there was surprising. Scattered around the facility were multiple orbital tank farm skids in various stages of completion. It quickly became clear that the Sidco facility had effectively been transformed into SpaceX's primary GSE prefabrication hub. And with multiple launch sites under construction simultaneously, that workload must have increased dramatically. At some point, likely between completing their final Starbase skids and responding to the emergency methane tank farm rebuild at Massey's, operations appear to have shifted yet again. This time to the Roberts Road facility. I could be wrong, but it looks like the Sidco team may have moved into the building originally intended for Starship production. At least I hope that's the case, and they're not sitting outside in the parking lot without shade, building 19 additional launch pads over the next decade. I'm happy to report, though, that before being sold to Blue Origin, the Sidco facility went out as an absolute legend. As far as I'm concerned, that is the birthplace of launch pad mass production. And while I do think they might be up for it, the new tenants certainly have some big shoes to fill. So, why does any of this matter? Well, if your goal is to mass produce critical GSE systems, it's extremely helpful to maximize the number of components you can manufacture in-house. Along with that, and perhaps more importantly, fabricating your own custom equipment allows you to do things that would otherwise fall outside of normal manufacturer specifications. And sometimes, those manufacturer specifications can impose limits that your system has no choice but to exceed. So now that we know who may be responsible for the madness we're about to uncover, let's walk through the evidence the same way that I had to do in real life. As much as I'd like to skip straight to the answer, that would completely erase the ridiculous amount of detective work it took to get here. And honestly, I think you'll understand the system a lot better if we piece it together the same way that we did originally. As the large pipe rack assembly was being installed in front of the vertical storage tanks, a second rack was constructed near the underground fluids bunker. That second rack would end up providing some important clues when it came to figuring out how the system actually functions. This large multi-level pipe rack is officially referred to as the isolation and purging area, but I'm going to call it the primary gas distribution manifold, or the HRAC for short, given its shape. Multiple high and low pressure gases are supplied to this distribution manifold from the main propellant storage farm. There, a series of hidden vaporizers converts the liquid commodities into gas and then stores them in a massive bank of high-pressure gas cylinders under the horizontal propellant tanks. From there, each of the individual high and low-pressure gas lines run along the backside of the blast wall. Looking at it from another angle, you can see that once it reaches the end of the wall, it turns down towards the ground. From here, it runs alongside the large concrete culvert carrying the main propellant distribution plumbing. After passing beneath the water tanks, they resurface underneath the top left corner of the HRAC. The rack itself acts as a major distribution hub, routing the various gases to the launch mount bunker, the integration tower, and towards the flame deflector storage farm. On the opposite end of the HRAC, there are 5 pipes that dive back underground and follow the buried trench I mentioned earlier. That routing tells us something important. The commodities stored in the vertical tanks, along with the 3 banks of high-pressure gas cylinders, are being supplied directly from the bulk storage system at the main tank farm. In other words, these systems aren't isolated, they can be refilled on demand, which is obviously critical for rapid turnaround times. At the time, we didn't know exactly which fluids and gases were being routed here, but the larger insulated line strongly suggested liquid nitrogen feeding the vertical storage tanks, We'll come back to identifying the remaining commodities shortly, because that detail will become more important later. As the pipe racks were being assembled, crews began installing enormous 24-inch high-pressure gas injection manifolds on top of the water tanks. Each manifold injects gas through 3 ports on the larger tanks and 4 on the smaller ones. When you compare that to the other Deluge systems, which typically use only 1 or 2 injection ports, it becomes clear that this system is designed to move a significantly larger volume of gas into the tanks. In early May, 2 small trenches were excavated in front of the smaller group of water tanks. Sections of 24-inch pipe, which would later connect to the gas injection manifolds for the 2 smaller tank groups, were buried there to allow long-term vehicle access across the area. Meanwhile, at the larger set of tanks, the high-pressure gas manifolds turned downwards towards the ground, where 4 capped flanges sit on top of what we assumed was a header manifold. Next to each of those flanges were prefabricated valve skids, which the ninjas at Sidco managed to somehow discreetly deliver to the site without us noticing. And that's unfortunate, because there are certain details we may never be able to confirm. But that was probably part of the plan. 5 more of these skids were secretly delivered the following week and placed next to the 2 underground pipe manifolds serving the 2 smaller groups of water tanks. Around this time, we began wondering whether SpaceX might eliminate the water recirculating vaporizers and instead use the high-pressure gas cylinders to push liquid nitrogen directly from the vertical storage tanks into the top of the water tanks. In theory, something like that could work, although for a number of reasons I won't get into today, it probably wouldn't be a very smart approach. But one thing was for certain. Whatever was replacing the 30,000-pound water recirculating cryogenic vaporizers was going to come in a dramatically smaller package, likely weighing less than 1,000 pounds. During that week's RGV Aerial Starbase Weekly livestream, we spent a lot of time speculating about what the missing component of that system might be. Those of you who watched that episode may remember Ryan Hansen's Space joking about placing Raptor engines on top of the gas manifolds and then using the exhaust to force the water out of the tanks. Like, what? But little did we know at the time how prophetic that joke would turn out to be. Knowing we should be on the lookout for something much smaller and more compact than what we saw at Massey's, I asked the team of CSI field agents in my Discord server to keep their eyes peeled for suspicious-looking packages arriving at Starbase. Those of you who follow Vix on X know that she's excellent at catching nearly every major development at the launch site. So, I wasn't at all surprised when she sent me this footage of some very interesting components arriving on one of the same trailers that had previously been spotted making weekly trips delivering components from Sidco. Between all the Lab Padre and NASA spaceflight cameras, this was the only angle we could find of them arriving, and unfortunately, it wasn't clear enough for us to make out any meaningful detail. So I reached out to NASA Spaceflight to see if they had any additional footage that hadn't made it into the multi-view stream. And sure enough, they found the perfect shot, just a handful of frames as the trailer passed in front of the build site. For a while, this was all we had to work with. You might be wondering, what can we possibly learn from a quick glimpse like this? Well, quite a lot actually. Even at low resolution, you can clearly see a large pipe flange on the bottom, a medium-sized flange on the side, and at least 2 smaller flanges on the top. And even without zooming in further, the first thing that comes to mind when looking at this geometry is a combustion chamber. But surely not, right? Why would something like that be needed anywhere other than on a vehicle? After arriving at the launch site, the GSE team wasted no time installing these units on top of the large gas distribution manifolds. Once we confirmed their final destination, I asked Starship Gazer to capture high-quality images of anything that might help us solve this mystery. And as usual, he didn't disappoint. Starting with the pipe rack assembly, we can clearly see the insulated liquid nitrogen line, but alongside it are 4 additional uninsulated lines feeding the same area. Thanks to visible labeling, we can identify them from left to right as high-pressure GOX, a green pneumatic supply, an unlabeled line, and high-pressure GN2. Now, that may have seemed out of order, but when I say from left to right, I'm actually referring to how they're laid out in the underground culvert. Once they re-emerge out of the ground, they're still in the same order. This makes it a lot easier to trace them to their final destination so we can identify where each commodity is stored. The high-pressure GOX runs to a control panel in front of the short stack of gas cylinders, while the GN2 line runs to a larger bank stacked beside it. The pneumatic supply runs to a control panel on the side of the high-pressure nitrogen tanks before splitting into 2 separate lines that run across the pipe rack. For the purpose of reverse engineering this system, the pneumatic supply is relatively unimportant. As a general rule of thumb, it's exclusively used for supplying valve actuators. One line feeds all of the valves in the liquid nitrogen area, while the other is for all of the gas generator skids. That leaves the final unlabeled line, which turns back underground and then disappears. It then resurfaces next to the control panel in front of the third set of high-pressure tanks on the opposite side of the farm. Before the new mega bunker was constructed and blocked the view from outside of the entrance, a conveniently timed shot of the control panel in front of those tanks confirmed what we suspected: high-pressure gaseous methane. And once methane appears next to high-pressure oxygen on the same manifold, there's really only one logical conclusion. These weren't vaporizers, they were Methalox-powered gas generators. I don't know if I can properly convey my reaction to how crazy this idea felt when I first realized what was going on here. And if you saw my post on X, or heard it quoted in Marcus House's episode from that week, then you already know where the term Baby Raptor came from. In retrospect, that's probably a terrible name, because I don't think these things actually have any moving components. And just like Booster Bidet and virtually every other name I've come up with, Ryan Hansen Space deeply despises it. So in order to convince him to help me with this episode, I promised that we would try to come up with something better once we fully understand how they work. Thankfully, by some miracle, these happened to be installed in a location that was visible from two extremely limited angles. This allowed Starship Gazer to capture the first clean images of these things out in the wild. With that said, we've officially reached the fun part, because it's time to reverse engineer these baby Raptors. And with one exception, we're going to do it entirely based on external features. The first thing to note is that this mysterious contraption appears to be divided into two distinct subassemblies. This includes a large canister bolted onto the gas discharge manifold, which we assume is the combustion chamber. On top of this is a removable lid with a relatively small dome in the middle. We quickly identified this as the Methalox gas burner. In my opinion, this is the most interesting component, so let's start there. Looking at it from the front, we can see two large pipe flanges extending from the side of the dome. As you can probably guess, these are the main gas supplies to the burner. But to determine which is which, we need to go back to the aerial view and quickly trace this out. Looking at the two banks of high-pressure gas cylinders, we know that GOX is distributed through a medium-sized pipe in the middle of the rack. If we do the same for methane, we can see that it's routed through a smaller pipe which runs adjacent to the high-pressure GOX. Zooming in, we can actually see weld lines identifying T-fittings, which tells us where the supply for each of the individual control skids branch down from. So when we look at this from the direction of the wetlands, oxygen should be on the left and fuel is on the right. From the ground angle, we can trace these lines to the large control panel. Here we see the GOX attached to the inlet of a ball valve, while the methane is routed to an identical valve below it, which is just out of view here. These lines continue to the inlets on the side of the gas burner. If viewing this from the highway, the GOX inlet would be on the left and the methane is on the right. This allowed us to confirm that the GOX enters through the upper inlet, while the methane turns downward and enters the dome from a lower position. One detail that immediately stands out is the dark ring around the dome, which looks like it's been exposed to significant heating. Based on the visible weld lines, there appears to be a component sandwiched between the top of the dome and the short cylindrical section below. In other words, these are three separate components joined together. What we are most likely seeing is an internal divider plate that splits the dome into two isolated chambers. Returning to the opposite angle, we can see two pairs of instrumentation ports tapping into the dome. One set is above the double weld line, and the other is just below it. Each pair includes a pressure transducer mounted vertically on a T-fitting, along with a temperature sensor on the horizontal branch line. The temperature sensors, or thermocouples, likely have long probes that extend into the center of the dome to capture accurate readings of the incoming oxygen and fuel flow. Monitoring pressure and temperature in both locations further supports the idea that the dome is divided into two separate header chambers. These chambers act as internal manifolds, directing oxygen and methane into the combustion chamber below. How those gases are delivered into the combustion chamber is the next question we need to answer. Without being able to see the internal components, we began experimenting with a few different injector concepts until we finally settled on an initial working design. For GOX to reach the combustion chamber, there must be some kind of injector passing through the methane header below. So extending from the GOX chamber, we envision a series of hollow tubes delivering oxygen directly into the combustion chamber. What we're less certain about is how the methane is introduced, so we considered three different possibilities. The first option was the simplest: small holes drilled into the lower plate, centered between the GOX injector tubes. Depending on the combustion ratio, those methane ports would likely be slightly smaller than the oxygen injectors. In this configuration, you'd have relatively isolated streams of each gas entering the chamber and mixing just before or during combustion. The second option was a coaxial nozzle design with a smaller GOX injector tube nestled inside of a larger perforated sleeve. Methane would enter through perforations drilled at a downward angle through the sleeve and flow alongside the oxygen injector until both gases enter the combustion chamber together. It would probably end up looking like these RS-25 injectors from below. In this scenario, the GOX stream would essentially be surrounded by methane, resulting in significantly improved mixing. Of the three options, this is likely the most difficult to fabricate and assemble. Taking that concept one step further, a third idea was suggested to us by the space engineer. It's actually very similar to the coaxial design, but the inner tube is removed. Near the bottom of the injector, the diameter increases to form a dedicated mixing chamber. Instead of drilling the holes at a downward angle, in this version they're arranged in a spiral pattern around the chamber. This introduces the flow tangentially, generating a vortex inside of the mixing chamber. The swirling motion promotes more complete mixing before the gases even reach the combustion chamber. Realistically, this type of swirl mixing feature is more beneficial when injecting liquids, and may not be strictly necessary when mixing gases. But in my opinion, this is the coolest of the three concepts, so that's ultimately the version we went with here. One thing to note is that this design would likely be much less forgiving when it comes to pressure balance between the two gases. You'd have to be extremely careful to prevent GOX from overpowering the methane and pushing oxygen into the lower chamber. This would also be an important consideration during shutdown. Unlike the shutdown procedure for a Raptor engine, they would not want to allow residual combustion to continue inside of this confined space after the gas supply is turned off. This would not only risk allowing oxygen and methane to intermix inside of their respective chambers through the holes in the injector tubes, but it could also potentially send a flame front traveling through the large discharge manifold. To avoid that, the shutdown sequence needs to be a bit more aggressive and instantly stop the combustion reaction. The best way to do that is to immediately purge the entire system with an inert gas as soon as the oxygen and methane valves are closed. In the ground images, we can see a small gas line entering the top of the oxygen chamber, and from the opposite angle, there is another one entering through the side of the methane chamber. This is very difficult to spot among all of the overlapping components. These are most likely high-pressure GN2 injection ports used to purge both of the header manifolds and the combustion chamber below. Anyway, we kinda got a little ahead of ourselves there talking about things that happen during shutdown when we haven't even turned it on yet. So now that we have a dangerously energetic mixture of Methalox flowing into the combustion chamber, it's time to provide an ignition source. Returning to the gas generator control skid, we can see a small pipe tapping off of the high-pressure methane supply and running into a three-way splitter. On one side of the splitter is a pressure transducer, while the other side turns down towards the bottom of the panel. There's an identical one tapping off of the oxygen supply as well. While we can't see exactly where these route to on the skid, it's safe to assume that they feed the collection of solenoid valves mounted on either side of the smaller control panel. From there, the smaller lines run up to the top of the lid where they split in different directions. It's hard to make out the details, but we can clearly see a component protruding out of the top with three lines connected to it. That's almost certainly one of two igniters penetrating through the lid into the combustion chamber. Just like the Raptor engines, these torch igniters require gaseous oxygen and methane. Naturally, we should expect the third input to be some kind of spark plug, or a high-pressure nitrogen inlet to purge the igniters after usage. But when we trace this third line, it appears to be connected to another transducer to monitor the pressure inside of the igniter. The fact that we can see two of these transducers sticking out from the lid is actually what tipped us off to the existence of the second igniter. Given that we don't see any other obvious inputs, that raises the possibility that they could be using an acoustic ignition system, where resonant pressure oscillations inside of the chamber generate localized heating intense enough to initiate combustion. This is similar to what we suspect is being used in the new Raptor 3s, so instead of going into further detail, I'll just save it for a future episode. Once the main Methalox injectors are activated and the flame is established, the reaction should become self-sustaining. So it's possible that the igniters are not run continuously, but are only used to initiate combustion from the main injectors. Of course, that probably requires a bit of precision control from the injector system to prevent a flameout during operation. So it might actually make more sense to leave them running just in case. But more on that later. By this point, we've established that there are more than likely no moving components in this system. And since the name Baby Raptor kind of implies that there's some kind of turbo machinery inside of the burner, I think we should all agree to never call it that again. Well, I guess you win this round, Ryan. Alright, now let's move on from the Methalox burner to the second component of this nameless gas generation system. With a steady torch burning inside of the combustion chamber, these Methalox combustors begin producing an enormous amount of thermal energy. And just like the water recirculating heat exchangers, that energy is used to rapidly vaporize liquid nitrogen on demand. As we've already established, the liquid nitrogen is supplied by the vertical tanks, which are pressurized by high-pressure nitrogen gas cylinders. This eliminates the need for mechanical pumps to control LN2 flow as it's discharged from the tanks. Instead, each set of tanks has its own control skid that splits the incoming supply between two pre-valves. From there, the gas is split between 4 smaller valves, which are the ones actually responsible for managing the flow to the tanks. Just think of it like a potato gun with 2 safeties and 4 triggers. This setup should give them at least 4 discrete flow settings: 25, 50, 75, and 100%. The combined output from each pair of tanks is routed to an insulated discharge manifold on top of the pipe rack. Instead of a single common manifold, the manifolds are split to isolate the supply from each group of tanks. The supply from the 2 larger tanks exclusively feeds the 4 gas generator skids dedicated to the dual flame deflector system. That makes sense considering that those tanks are more than double the volume of the other 2 groups combined. The manifold from the smaller group of tanks spans the remainder of the pipe rack and feeds the 2 gas generator skids for the Apex system, followed by the remaining 3 for the water-cooled launch deck. If we look closely at the space between the sections of insulated tubing, we can see weld lines identifying 10 T-fittings tapping off the common supply. This means that while there are currently only 5 gas generators installed on this side, the system was clearly designed with expansion in mind. More specifically, it appears arranged to support 3 additional units for the Apex system and 2 more for the launch deck. So if they ever decide that they want the fountain from the water-cooled deck to reach all the way to South Padre Island, they may actually be able to pull that off. Connected to each of the T-fittings on the discharge manifold is a braided flex hose that runs down to the gas generator skids. After passing through a set of double isolation valves, the liquid nitrogen supply connects to a large flange on the side of each gas generator. That inlet flange ties into a circular manifold between the top and bottom halves of the cylindrical chamber. Without being able to see the inside of the container, we believe there is no inner radius to this manifold. Instead, it's basically a part of the outer shell. We don't see any exhaust stack for the burner, which means this isn't functioning as a traditional heat exchanger like the water recirculating vaporizers. Instead, the exhaust appears to be fired directly into the high pressure flow of liquid nitrogen. For that to work, the liquid nitrogen has to be introduced in a way that prevents it from choking out the flame. If we look just below the cap on the top of the combustion chamber, we can see another thick weld line indicating that there's an additional internal component. We believe there's a smaller radius cylinder inside of the chamber with a flange welded to its top. That inner cylinder effectively becomes the combustion chamber, while the outer cylinder forms a liquid nitrogen jacket around it. To control the flow of liquid nitrogen into the combustion chamber, hundreds of holes are drilled through the wall of the inner cylinder at a downward angle. As the liquid begins flowing into the manifold, it fills the outer jacket from the bottom up and then sprays inward through the side of the combustion chamber, where it meets a column of hot exhaust gas. As you can see in the following simulations, Ryan designed this with the holes pointing towards the center. This is one of the only disagreements him and I have on this topic, and personally, I suspect these holes are arranged in a downward spiral pattern so the liquid is spraying towards the walls instead of towards the middle of the combustion chamber. This would form a large vortex as the liquid nitrogen begins flowing into the chamber. As a result, it would create a cone-shaped void for the burner to fire down into, which would allow for more complete combustion. But from a manufacturing standpoint, Ryan's design is much easier to machine, and with all the holes pointed towards the center, the opposing liquid jets would collide near the middle of the chamber, potentially improving atomization and mixing. So there are clear trade-offs here, and depending on which design priority matters most, this may actually be the better option. Either way, the basic concept is the same. We're using a massive torch to rapidly vaporize liquid nitrogen. And with a 694:1 expansion ratio, that interaction doesn't just produce gas, it produces an explosion of volume. That rapidly expanding nitrogen is then redirected into the tops of the water tanks, where it begins forcing water out under immense pressure. As you can probably imagine, these things aren't exactly quiet during operation, but we will see that shortly. Before we move on, there's one more feature that is extremely important that we would otherwise be completely unaware of without an incredible stroke of luck about 1 week before Part 2 was released. So huge shout out to Alex for catching this. If you've ever tuned in for one of the RGV Starbase weekly live streams, then you've definitely met Alex. During that week's flyover, Alex happened to notice a random headless gas generator sunbathing on a pallet inside of the entrance to the Sanchez site. I'm honestly not sure if they're doing this stuff on purpose, but it sure feels like it sometimes. Anyway, you can probably guess what happened next. Thanks to Starship Gazer, we can now see the only existing image showing the internal components of this system. When we zoom in as far as possible, you can actually see the internal sleeve with all of the perforations through the wall. It's nearly impossible to tell whether or not they're drilled at an angle, but at least we got confirmation that Ryan's design was about as on point as it could get. But more importantly, when we zoom out, we can see the source of the 4-week delay for releasing this episode. a pattern of 12 large nozzles extending out from the side of the combustion chamber in a spiral pattern. This discovery fundamentally changed our understanding of how these gas generators work, and forced me to reevaluate my analysis of everything we cover from this point forward. Even worse, it also forced Ryan to completely redo a simulation that basically took 3 weeks to render. In other words, this was a very big deal. On the outside of the wall, we can see the inlet port for what is apparently a secondary internal manifold. Now that we know what to look for, we can actually return to the previous angle and see another internal weld line thanks to the discoloration. Ryan interpreted this as a 1/4-inch disc around the inside of the liquid nitrogen jacket that creates 2 isolated compartments. I admit this may seem like a lot to infer just based on an external discoloration pattern, but the interpretation starts to make more sense when you think through how this container would actually be assembled. Starting off, we have the combustion chamber welded to a large flange on the bottom. At the bottom of the chamber, before it tapers outwards to meet the flange, there is a circular plate creating the bottom of the outer shell. Next, the outer shell wall and ring manifold assembly would be lowered over the combustion chamber, resting on that bottom shell plate. Once centered, it would be welded around the bottom perimeter to lock the shell in place. From there, the annular divider plate would be dropped in from the top and welded around both its inner and outer circumference. That internal weld line is what we're seeing from the outside. Once that weld is complete, the top plate flange is added to close out the container. As you can see, this flange has a double set of grooves milled into the surface that allow gaskets to be placed in both locations, creating a seal between the combustion chamber and the lid. Initially, we believed this newly discovered internal manifold was part of a 3-stage purge system, one in each gas chamber and then a third for the combustion chamber. But since Ryan believed that this was way too large to be a gas injection port, I went looking for additional evidence. After scanning through 9 months of aerial images, I found a single week where this feature was visible from the right angle. Here we can see that between the double isolation valves for the liquid nitrogen, there is a small pipe tapping off of the main supply, and we can trace that line out to the small inlet on the top of the combustion chamber. So not only does that confirm that this is liquid nitrogen, but it also explains why there are 2 isolation valves here. This secondary system is meant to be activated some unknown length of time before the second valve opens and it begins sending a much larger volume of liquid into the shell. That makes its purpose fairly easy to figure out. This is basically an internal cooling system for the combustion chamber that likely remains active the entire time the burners are running. Since these nozzles are arranged in a spiral pattern, when they turn on, it will look very similar to the Raptor QD nozzles on the R&D launch mount. But instead of converging in the center, it will leave a huge hole that's about the same size as the injector plate on the burner. Without the massive Methalox torch running, this will create a liquid vortex that hugs the perforated walls of the combustion chamber. Once the burners are activated, that liquid would quickly transition into a gas, creating a continuous protective layer between the chamber walls and the hot exhaust flow. From here on, I'm going to refer to this operating state, where the cooling system is active on its own, as idle mode. Not only does idle mode allow the burner to run for extended periods without the main liquid nitrogen system active, but it also reduces thermal shock to the inner walls when the system transitions into gas generator mode and that much larger volume of cryogenic liquid begins flowing. Now that we understand how this system works, the real question becomes, okay, but why? Why go through all of this trouble? If the water recirculating vaporizers were already working well enough to be worthy of duplicating the system at McGregor, then what's the point of replacing them with something this aggressive? Before we see this thing in action, we need to know why it exists in the first place. So to answer that, we need to look at 6 factors: cost, convenience, complexity, reliability, recycle time, and overall performance. From a cost standpoint, these units are clearly designed and manufactured in-house. That alone likely makes them dramatically cheaper to produce and maintain. When you're building out 4.5 launch pads simultaneously, even small savings scale fast. In terms of convenience and overall packaging, this replaces a 30,000-pound water recirculating vaporizer with something roughly the size of a trash can, and likely weighing less than 1,000 pounds. It's dramatically lighter and more modular, although once you factor in all the auxiliary systems, the total footprint probably ends up similar for all 3 systems that we've looked at. Unfortunately, when it comes to complexity, that's where this system earns the kind of F that takes up the entire width of a standard regulation-sized report card. Compared to a gravity tower or even Pad 1's booster bidet system, where you open up a few valves and let physics do the work, this is an orchestration of sensors, actuators, feedback loops, and tightly managed combustion. It's kind of like going from a bottle rocket where you light the fuse and hope it goes straight, to a long-range, surface-to-air precision-guided missile with active thrust vectoring, inertial navigation, real-time telemetry, and data link targeting updates. That added complexity almost certainly increases the number of potential failure points. When it comes to recharge time, the answer isn't entirely clear. They still rely on high-pressure gas cylinders for tank pressurization, and now they've added methane and oxygen storage on top of that. So in terms of eliminating hardware they didn't like, you could argue that they're back where they started. But that's missing the point. The real advantage of this system is performance. The first aspect of that performance advantage, which you will definitely notice here in a few minutes, is the overall responsiveness. Relatively speaking, heat transfer inside of a WRV is kinda slow, which is why it requires roughly 60 feet of coiled tubing submerged in warm water just to complete the phase change from liquid nitrogen to gas. You're relying entirely on surface area and a finite temperature difference to get the job done. With these new Raptor hatchlings, with these new gas generators, you're no longer relying on passive heat exchange across metal walls. You're dumping combustion energy directly into the fluid stream and using brute force to do something that would otherwise require a 225-ton radiator assembly. Both the activation and response to changes are damn near instantaneous. There's no gradual ramp up. As soon as they light, it's 0 to 100. Kind of. That responsiveness alone is impressive, but not the biggest advantage. The biggest advantage is thermodynamic efficiency, and more importantly, controllable thermodynamic efficiency. For the sake of comparison, let's assume the liquid nitrogen mass flow rate is the same in both systems. In other words, you have the same amount of liquid nitrogen entering both devices. The only variable we're changing is how much energy we inject into it. As I just said a few minutes ago, the commonly quoted expansion ratio for liquid nitrogen is 694 to 1, meaning 1 gallon of liquid nitrogen becomes 694 gallons of gaseous nitrogen at atmospheric pressure. But that figure assumes that the final gas temperature is a little bit warmer than room temperature, about 300 Kelvin. In reality, that ratio is entirely dependent on the final temperature of the gas. When liquid nitrogen transitions into a gas, there are actually two compounding stages of expansion. First is the phase change at 77 Kelvin. That alone increases the volume by roughly 175 times due to the massive drop in density. Then comes thermal expansion. As the gas warms from 77 Kelvin to its final temperature, the volume increases proportionally with the absolute temperature. In the case of the WRVs at Massey's, the water bath is specified at a minimum of 50 degrees Fahrenheit, or about 283 Kelvin. However, as we saw in the example with the smaller heat exchangers used in the original tank farm bunker, those systems can be equipped with water heaters. While I haven't seen any evidence of water heaters being used either here or at McGregor, the manufacturer specifications allow for bath temperatures up to roughly 150 degrees Fahrenheit, or about 339 Kelvin. If we assume the nitrogen exits near the lower end at 283 Kelvin, warming from 77 Kelvin to 283 Kelvin produces a thermal expansion factor of about 3.68. Multiply that by the 175x phase change expansion, and you get a total expansion ratio of about 643 to 1. If we instead assume that the bath is heated to its upper limit of 150 degrees Fahrenheit, or 339 Kelvin, the expansion factor becomes about 4.4. That yields a total expansion ratio closer to 770 to 1. Even under that best-case WRV scenario, the system remains fundamentally limited by the maximum achievable water temperature. Now compare that to the gas generators. Instead of a 50-degree water bath, you have a continuous column of combustion gases potentially ranging from 1300 to 2000 degrees Fahrenheit. And unlike the passive system, the burner output is adjustable. You're not limited by coil length or bath temperature, you're limited by how much Methalox you're willing to burn. If the nitrogen is heated to around 750 degrees Fahrenheit, roughly 672 Kelvin, the total expansion ratio climbs to approximately 1,704 to 1. Under the same liquid nitrogen mass flow rate, that means the gas generators produce more than 2.2 times the volume of pressurizing gas compared to the WRV example. That's not incremental, that's a cartoonishly large increase in volumetric output. But wait, there's more. In a WRV, the nitrogen is isolated from the water. In other words, nothing is added. What goes in as a liquid comes out as nitrogen gas, and that's it. In the gas generator system, the combustion products, which are primarily water vapor and CO2, are injected directly into the nitrogen stream. And it's worth mentioning that depending on how hot and oxygen-rich they're running the burner, this direct vaporization could also create a very favorable environment for secondary reactions that form nitrogen oxides. which is not necessarily something you want to happen if it can be avoided. So that is something to consider. Those combustion gases can account for an additional 5 to 10% of the total output. So you're not just heating the nitrogen more aggressively, you're increasing total mass flow as well. Same LN2 in, far more usable gas out. And you can tune it in real time. In a way, it's kind of like bolting a supercharger onto the entire system. But theory is one thing, and while a massive increase in thermodynamic leverage sounds absolutely fantastic on paper, the real question is, does it survive contact with reality? On that note, I think it's finally time for us to see these things in action. Now, even though these gas generators were fabricated and potentially designed in Florida, the high-energy testing required to certify them for use at Starbase could only have occurred at McGregor. With that said, I'm fairly confident these gas generators must have undergone a full range of function and acceptance testing a decent amount of time before we actually became aware of them in June of 2025. There's simply no way they committed to something this extreme without validating it first. But, if I'm being honest, I can't actually find any proof of that. The first test we were actually able to witness took place 1 month after all 9 units had already been delivered to Starbase, which is pretty wild. The native audio is fairly quiet, but after enhancing it and syncing it with the footage, you can hear that it clearly sounds like a static fire test of a very small Methalox engine. The following month, Gary Blair with NSF performed a flyover of the facility and captured images of the new test stand. Zooming in, we can see what appears to be a gas generator mounted on top of an exhaust manifold, with the outlet pointing straight up. The methane and oxygen lines are routed to the burner from below the raised platform, with several control panels mounted along the wall. From the opposite angle, we can see what appears to be a logo similar in style to other team markings we've seen around Starbase. I could be mistaken, but this looks like the silhouette of a grackle. These loud, obnoxious birds are literally everywhere in Texas, and given that SpaceX tends to name its engines after birds, like Merlin, Kestrel, and Raptor, this would be very on brand. So until we hear otherwise, I'm going to go ahead and assume that this is the internal designation for the combustor used in these gas generators. Before we take a closer look at this test, there's one more detail worth pointing out. Directly behind the gas generator, we can see a small tank that is most likely for liquid nitrogen storage. Next to the GOX and methane inlet valves, there is another red actuator of similar size. From the available angles, we can't see the large flange for the main LN2 inlet on the chamber. So this valve could either feed the primary LN2 supply or the spiral nozzles for the internal cooling system. When we look at the test footage, I think that question answers itself. The first event we see is a cloud of vapor being expelled from the exhaust stack. Based on what we know about the system, this is likely the spiral nozzles activating alongside an initial nitrogen purge. The exhaust manifold is sitting at ambient temperature, so the liquid nitrogen rapidly boils off on contact. But with no additional heat being applied, the resulting vapor remains relatively cool, which is why the plume appears dense and opaque. Once the grackle is ignited, the exhaust immediately transitions into a hot, fast-moving plume with intermittent flashes of vapor. I'm going to loop this footage a few times while we try to figure out what's happening. There's no way to know for sure, but something is clearly causing the plume to cycle between hot, mostly invisible exhaust, and cooler, visible vapor. If we overlay the audio waveform, it does appear that something is modulating during this sequence. But on its own, that doesn't tell us what's actually changing. So I think there are two possible explanations. One possibility is that they are adjusting the flow of the spiral nozzles during operation. If that's the case, increasing and decreasing the liquid nitrogen flow could alter both the visible plume and the acoustic signature. Increasing the amount of gas being generated can partially suppress or mask the sound of the exhaust. In that scenario, they may be trying to find the setting that maintains a stable combustion chamber temperature or stress testing the grackle to see how it responds to sudden changes in internal cooling flow. In other words, making sure the liquid nitrogen doesn't accidentally smother the flame. The second option is that they are adjusting the pressure and therefore the thermal output of the burner itself. Changes in combustion intensity would directly affect both the plume visibility and the acoustic output, which would explain the modulation we're seeing in the waveform. But this of course assumes they actually have the ability to throttle the output, which we haven't actually confirmed yet. Looking back at the control skid, the GOX and methane valve actuators appear to have simple position indicators on top rather than smart valve position controllers capable of regulating flow. So unless there's additional regulation happening somewhere we can't see, These valves are likely limited to either fully open or fully closed states. But upstream of each valve is a mysterious canister with a small pneumatic supply running to it. I have no idea what this is, so if anyone recognizes it, let me know in the comments. The fact that it has a pneumatic supply suggests that this is not a simple pipe fitting, but some kind of custom mechanical component. My best guess is that this is a pressure regulator or flow control device that I haven't seen before. Since this component is present on both the oxygen and methane supplies, there's a good chance that the burner output is adjustable after all. In my opinion, that explanation seems more likely, but we'll revisit that idea a bit later. Now, you may be wondering why I'm not factoring the primary LN2 supply into these observations. Well, that's because I'm fairly confident that it isn't active here. I think you'll come to that same conclusion once we look at some additional testing footage. In my opinion, there's a strong possibility that this test is completely unrelated to the water deluge system and is instead a standalone test of the Grackle combustor simply making use of the internal cooling system on the gas generator canister. Anyway, as soon as the burner shuts down, the cold nitrogen vapor becomes dominant again as the spiral nozzles continue running while the system is purged. If you look closely, you can actually see rotation in the plume, which is likely caused by the vortex generated by those spiral nozzles. Even though I personally do not believe that this is deluge related, the timing of this test is actually pretty interesting. 19 days later, the brand new vertical test stand, Raptor North, conducted its first static fire. And after just 4 static fire tests in the first month, the water storage tanks went from looking pristine to looking like this. Yuck! When we compare that to the Raptor South test stand, you can see that it's clean as a whistle. Even though this detail had been sitting in plain sight for months, it wasn't until I started gathering evidence for this investigation that I truly noticed it. Because up until that point, I had assumed that the 2 deluge systems were identical. But these stains were basically the universe waving a giant brown flag and telling me that I probably needed to give this a closer look. Now, to be fair, one possible explanation is that this is really just dirty or rusty water spraying out of those vents. And when we look at the water tanks at Massey's, we do have a good example of what that kind of staining looks like. In that case, the pattern is clearly from dirty, atomized water spraying out of the vents. But this looks different. The stains here do not look like random watermarks. It looks more like soot deposition, or possibly the result of extremely hot gas venting out of these ports, burning away some of the paint and allowing the exposed steel beneath to start rusting. The pattern also seems to follow something closer to a temperature gradient, which matters because there are no extreme heat sources involved in a normal water recirculating vaporizer system. Now, when we look at the location where we should find a WRV on the north stand, there's nothing there. I've looked at this from every available angle, and at first, it was very difficult to determine how this particular deluge system was operating. Out of all the early images of Raptor North, this was the only one that provided any clue. And it wasn't clear enough to say with complete certainty, but it looked like there may have been at least one Grackle-powered gas generator hiding in front of this vertical liquid nitrogen tank. Fortunately, as I was recording this, we got lucky with one of the most recent flyovers, where there were images of Raptor North taken shortly after the conclusion of a static fire test. Thanks to the frost buildup on the liquid nitrogen manifolds, we can now see that there are actually 2 gas generators installed on this test stand. So with that in mind, Raptor North was likely the guinea pig for commissioning this new system. And based on the staining around those vents, it looks like something may have gone very wrong during those early tests. The simplest explanation is that hot combustion products were venting out of those outlets, either depositing soot, burning away paint, or both. A more speculative worst-case scenario is that this wasn't just hot gas, but it may have actually been an open Methalox flame coming out of the vents. And while there's no way to verify this, it's at least worth considering because of how this system appears to operate. If the burner were extinguished for some reason during startup or liquid nitrogen injection, and the system didn't react fast enough, unburned methane and oxygen could continue flowing into the gas manifold. If that mixture later found an ignition source, whether from a relight attempt or from the second gas generator, it could send a flame front propagating through the system. If that were to occur, the flame would have nowhere else to go, and those vents would be the only available escape path. If that's the case, I really wish there was footage because that would have been incredible to see. Before we continue, since Marcus House asked, and I never really gave him a proper answer, I want to acknowledge that the testing that we observed at McGregor may be completely unrelated to these water deluge systems. That's why I've been careful to say that the name Grackle applies specifically to the combustor. Based on how it's mounted to the top of the chamber, it looks like a modular component that could be used in multiple configurations. A few months after that test, the stand was reconfigured and another Grackle unit was added downstream from the first. From another angle, it appears to be mounted directly to the exhaust manifold without the combustion chamber. Another important change is that the nozzle for the exhaust was no longer pointed vertically. It's now rotated horizontally and aimed directly at a flat panel mounted between 2 posts. Behind that panel, There's also a flat table with what appears to be TPS tiles mounted on top of it. And given that both Grackle units are attached to the same exhaust manifold, they're likely being run simultaneously. The only other test we've noticed since that first one occurred in January of this year. Now, it definitely sounds a lot different from the original test, but based on the location and audio, we believe it may come from the same test stand. As I've hinted at multiple times now, there's a very good chance this hardware is also being evaluated for other applications as well. Rapidly vaporizing cryogenic fluids has several potential use cases, and one that immediately comes to mind is onboard propellant gasification. For example, a system like this could potentially be used on Starship to vaporize liquid oxygen or methane and generate ullage pressure for propellant transfer between tanker and depot variants. Oddly enough, the space engineer pointed out another adjacent test cell constructed between this pair of concrete walls that may be related to that exact concept. This appeared a few months after the Grackle test stand, and leading away from the test cell are a pair of horizontal vents. One of them appears to have a pilot burner in the middle, suggesting it may be some kind of methane vent. Looking at it from the front, we can see a fairly complex panel with a ton of components mounted to it. Unfortunately, this isn't a clear enough image for us to make out too many details, but we can see an insulated line entering the top of what appears to be a small turbo machinery assembly, along with another line that could be carrying hot gas and a potential vent for purging the system after operation. I'll probably save this topic for another time or let the space engineer cover it, but one possibility is that this system is using a similar combustor concept to vaporize propellant before sending it back into the tank, basically creating an autogenous pressurization system that does not require running a Raptor engine to boost ullage pressure. A second test stand was added sometime in February, which featured a slightly different setup, possibly suggesting that one of these is for gasifying methane while the other is for oxygen. That would explain the two vents leading away from the test area. In a flight-like system, those gases would be routed back into the vehicle tanks for autogenous pressurization instead of being dumped overboard. If this is what we think it is, then this would be another sign that HLS development is progressing well beyond what most people assume. And on that note, there is a possibility the second test I pointed out could be coming from one of these two test stands. Although, based on the direction the plume seems to be traveling in this grainy footage, we don't believe that to be the case. Speaking of HLS, another potential use case could be HLS thruster development. In theory, these units could be integrated with a combustion chamber built into the sidewall of the HLS payload section. There's nothing obviously preventing that, aside from potential differences in fuel mixture ratio requirements, gas injection pressure, and whether additional cooling would be needed. The high-pressure GOX and CH4 would be supplied by the COPVs already on board the ship. But here's the problem with trying to trace this back through HLS. Right now, HLS mostly exists as renders, mock-ups, and system-level test articles. So unless SpaceX rolls out a ship with one of these thrusters mounted to it, I don't think we have enough information to draw any meaningful conclusions from that comparison. But there is another option if we're trying to track down the family tree. And weirdly enough, it takes us all the way back to Booster 3. Long before the modern cold gas RCS system, which uses ullage gas from the tanks for attitude adjustments, Booster 3 had hot gas RCS thrusters mounted onto the forward section. This might be a massive blast from the past for those of you who actually remember this. And when you look at them now, with the gas generator system fresh in mind, they start to look a lot more familiar. What you're seeing here are 3 RCS thrusters, 2 on the sides providing roll and yaw control, while the one facing outwards is for pitch adjustments. Now, looking at this absolute mess of pipes, we can kind of see the labels, but we don't really need them. Instead, I'm just going to take a wild guess and say that these are the methane lines routed into the side of each thruster, while those are the GOX lines routed into the top of the combustors. And it doesn't stop there. There are even sensors in a lot of the same locations as what we see on the Grackles. The biggest difference is really the form factor. On Booster 3, this had a nozzle bolted onto the end because it was supposed to generate thrust. On the Deluge system, that nozzle is replaced by what is essentially a liquid nitrogen flame tube. Because the goal is not thrust, it's dumping a ridiculous amount of thermal energy into LN2 as fast as possible. So, in my opinion, this seems even more likely to share some design lineage with the Grackles than the HLS thrusters. And honestly, that would make a lot of sense. Of course, just to be clear, there's absolutely zero evidence proving that connection. So that's about as far as I'm going to take that line of speculation for now. But you gotta admit, that would be a pretty interesting backstory.
It seemed to me that whatever loading of propellant they did, they have done. And the vehicle is in a steady state at this point, sort of waiting to do its thing.
Closeout complete. LOX bleed transducers showing stable pressure on all 3 engines. We are good to proceed. What's up, Victor? Surprised you made it.
Come on, Brandon. There was no way I was going to miss our first integrated test. I drove all the way down here 3 days ago just to double-check the install myself. How much time we got before T0?
We are 20 seconds out.
Dude, pull up the pad cams. Why you got this NSF stream on?
Well, our cameras might be better, but they don't have live commentary from 5,000 spectators in the chat. You should read some of this stuff, man. It's hilarious.
Oh, good point. I actually do want to see their reactions when they see the RCS thrusters go for the first time. Here we go.
Whoa. That's a good test. 3.52 seconds. Stand by for system checkouts.
What happened?
I'm not sure, actually. It looks like RCS was disabled.
Disabled? You mean like an abort? Which sensors failed, or was it one of the igniters?
No, this looks like a manual override.
What? From who?
Look, man, I'll try and get you some more info, but you may have to wait until the debrief in 3 weeks.
3 weeks for a debrief?
Bro, we can't even get this thing back off the test stand. It's welded down. Literally, as of 20 seconds ago, nobody even cares about B3 anymore. As soon as we finish detanking, everyone is shifting gears to Booster 4.
I care. I really need that data.
I'm not sure what to tell you, man. You're just gonna have to be patient.
Nah, man. Not even a single rumor. I haven't heard anything at all. That's the problem. The entire RCS team is basically in limbo until that meeting next week. Hey, let me call you back.
Anyway, we've got like basically a lot of gas in this thing, which we would have to actually just vent to vacuum anyway, because it's got too much gas.
Yep.
And that's just extra mass that you don't need.
Right.
So if you've got basically enough control authority because of the kicking the whole stack over before main engine cutoff.
No way.
Plus,
it is Timda.
Using the ullage gas to vent, then you don't need a separate hot gas thruster system. You don't even need a cold gas thruster system. You already have hot gas.
For the booster, right?
Delete the question the requirements, delete the part.
Yes. But this is only for the booster, right?
Yes. Although arguably, now you mention it, we might be wise to do this for the ship too.
What the?
How can you have? You'd think that because
at least mostly.
Well, we certainly have our work cut out for us, don't we? I think we should go ahead and wrap things up here, unless anybody has any final thoughts.
Seems like a good time to remind everybody that we do these things, not...
Charles, this is not the time.
Yeah, you're right.
Didn't see that one coming. Yo. You ain't gonna cry in the car on the way home for sure.
Damn. Oh, hey Drew, you got a minute? Cool. Yeah, I noticed that during the meeting, you didn't really mention anything about HLS. And, well, I was just wondering what the timeline looks like on integrating some of the hot gas thrusters into a test starter. You see, on my way in, I noticed that Ship 27 is still sitting out there in the rocket garden. And, I mean, unless we're doing something else with it, we might as well just pop a few of these in, right? I mean, look at this. I'm pretty sure that we could pull this off in less than 2 weeks.
I'm guessing you didn't hear what happened last night. 27 had a little accident. She's done. Matter of fact, if you got nothing better to do, you might be able to make it outside before they finish chopping her in half.
Damn. So...
Look, we gotta design a whole new launch pad, and we have 8 flights left to do it. With the amount of things we need to get tested in that time, ain't nobody thinking about HLS right now. You need to get your head in the game, Victor.
Hey man, you got anything stronger?
Yeah, what'd I give you the first time?
Dasani.
Oh, we just got some of that Fiji in. I know you want that.
Okay, yeah, that works.
Damn. I mean, damn, it's good to see you, dog. I thought I saw you at the meeting, but I almost didn't recognize you. Yo, what the hell happened? You look like you aged 10 years in the last 24 months. You good?
Yeah, I'm good.
Nah, he ain't good. This happens when you spend 2 hours at the end of every shift plotting revenge. You end up looking like Mojo Jojo.
For real, guys, I'm good. I mean, you gotta leave the past in the past, right?
Yeah, well, that's good to hear, man, because at the end of the day, I mean, you gotta admit, it technically wasn't even Tim's fault.
Man, Tim Dodd.
Wow. You got a lot of pent-up anger, buddy. If I was you, I would write him a strongly worded letter.
It's not enough.
Well, shoot, I don't know. Maybe even kidnap his ass and tell him to his face.
You might be onto something there.
Shoot, I'd do it for you.
Definitely don't do that. That's a terrible idea.
Well, I have to do something, man. I can barely sleep. You know, everything I've worked on over the past few years might all be for nothing. You know, that's why I'm out here. Just helping out where I can, trying to stay useful until things pick back up with the lander, you know what I mean?
Look, I feel you, man, but I think you need to get away for a while.
Yeah.
Out of McGregor, for sure. And I mean, here, walking past that HLS mock-up
Terrible.
every day has gotta be torture. Have you ever thought of going down to Florida for a little bit?
For what? Isn't 39 still delayed?
Well, actually, now that we gotta completely redesign the pad, they just put me in charge of organizing the biannual water deluge competition.
What's that?
Word on the street is, them boys at Sidco might actually try to take on McGregor.
Did you say
this year.
Sidco?
Hey, them boys are real. I think they could use all the help they can get. You should think about it.
Well, I mean, I did have this idea that I came up with a few years ago, but surely they wouldn't go for that.
Only one way to find out.
Okay. Yeah. I think I'll do that.
Honestly, we may never learn the true story of how these grackles came to be. But that's fine. Personally, I'm just happy that we've been able to figure out as much as we have. All right, everyone. As much as it pains me to end things here, we're going to have to pick up where we left off next time in part 4. I was really hoping to get that out before Flight 12, but hopefully you won't mind it being a little late. In that episode, we'll do a deep analysis of the isolated and combined deluge system testing. We'll take a closer look at SpaceX's methods for suppressing ignition overpressure and cover all of the integrated vehicle testing up to and including Flight 12, specifically as it relates to the deluge system. And as part of that, we'll examine what went wrong during the first 2 static fire tests that ended in pad aborts. I know many of you have been wondering about that, and I promise you will not be disappointed. With that said, make sure you're subscribed because you definitely won't want to miss part 4. Before we go, I want to say another massive thank you to everyone who donated through PayPal after the last episode. I just want you all to know that without your support, I probably would have capped this episode at around 100 minutes instead of extending it by another 80. And of course, that also goes for all of the new channel members and Patreon supporters as well. Just like last time, I plan to send the QC version of Part 4 to everyone as a thank you once it's ready, so be on the lookout for that. I also want to give another huge shout out to Knaggs for the incredible amount of work it took to model pretty much the entire Pad 2 flame trench, launch mount, and deluge farm. And also to Ryan Hansen Space, who spent way too much time modeling and simulating the gas generator system. I'm still shocked by how often he manages to pull off the ridiculous things I challenge him to. Last but not least, thanks to Starship Gazer, RGV Aerial, Lab Padre, NSF, and everyone else whose content was featured in today's episode. You can find the links to all of their platforms in the description below. Oh yeah, and good luck to the SpaceX team and Stage 0 2.0 during its big day coming up on Flight 12. Alright, that's my time for today. Can't wait to see you all in Part 4, and I think it'll be well worth the wait. Until next time, this is Stage 0 Zach, signing off.